Morning, Eduardo.
Good morning.
Kind of cold today.
Yeah, still snowing.
Good morning, Kennedy. Good morning, Lauren. There's a very good possibility, before we get started, there's a very good possibility that next week we will continue with no in-person attendance as long as this record cold snap holds out. No point in putting any of you to the hazard driving into campus and or walking across campus to get here after you get a parking space. We'll see how it goes. I'll post an announcement in Blackboard if I decide that for sure, but right now I'd say it's about 80% likelihood that we will not have in person at least through Wednesday of next week. Okay, it's time to begin. I want to go over 3 more factoring problems. And before we go over these, I want to mention you might want to get out the sheet that looks like this. Steps for factoring polynomials. We're going to be using these A, B, C, D, E rules right here. So you might want to get out that handout. Because that's what concerns these first 3 problems. Now, when we get ready to solve this problem, there are 2 ways we can do it. I mean, we can do it by the factoring method that I've been using, 1 times 25, 5 times 5. And in this case, it would be 5 times 5. So plus, so we're going to add, here I get a 5, here I get a 5, everywhere I get a 5. Which gives me a center value of 10. And of course, everything is pluses in this one. So here are my 2 products. Now, that's one way of doing this problem. The other way of doing this problem is by using that example A on the handout I just showed you. Now, I'm going to take a slight variation of that. First term squared plus 2 times the first term times the last term plus the last term squared. Okay? Well, in this case, the first term is just, this can be rewritten as 1x squared, and this can be written as 5 squared. So we now have this problem in that format for that example A. Now what this is saying, that rule that it gives us, says that this is equal to the first term plus the last term and the first term plus the last term, or first term plus last term quantity squared. Now that's what that's saying. Let's look at this thing in its numbers. We put in an x here, okay? And if this is true, then this would say that x, the first term, plus 5, the last term, times the first term, x, and the last term, or x plus 5 squared. This rule is saying that in this problem it should be true, but we've got to verify that it's true. Now, 1x is certainly the first term squared, and 5 squared is certainly the last term. Now, do the first term, x, times the last term, 5, times 2, equal 10? Well, yes, it does. That's the test of if this factoring shortcut will work. So if 2 times the first term, 2x times 5 equals 10x, then yes, it works. Let's prove this though. Let's FOIL this thing. X times x is x squared. Okay. 5 times 5 is 25. 5 times x is 5x. And 5 times x is also 5x. Right here is where that 2 comes from. Is because if this is a perfect square quadratic, then you will get 2 equal middle terms. So x squared plus 10x plus 25. Now, the trick to using this is recognizing if you have a perfect square on the front number, if you have a perfect square on the back number, then check to see if this is true, and you've saved yourself a lot of factoring work. Okay? Well, let's go through this same problem on the next problem. Is this a perfect square? Well, yes, it is x squared. Is this a perfect square? Well, yes, it is 7y squared. So we have a perfect square on both ends. Now we need to see if 2 times the first term times the last term equals this. Okay? Well, 2 times x is 2x, times 7 is 14xy. 7y, I should say. Okay? So this one is a candidate for using this shortcut. So my answer then is going to be simply x plus 7y quantity squared. Done. Now let's go to my third example. I have something a little different here. I have a minus in the middle. Now, if you look at example B on that handout sheet I gave you, then the rule fits for it. So theoretically, since I have a perfect square on the front, 8z squared, and since I have a perfect square on the back, 1t squared, then I could use that rule B, which said my answer should be first minus last quantity squared, if the middle term verifies. Well, is 2 right here plus or minus for rule A or B. Okay, 2 times 8z is 16z times 1t is 16zt. So it checks. So my answer then is 8z minus t quantity squared. Okay? And those are perfect square binomials, either with a plus here or a minus here. And that's certainly a shortcut you can use. Now, the conjugate shortcut, we'll go over it briefly. The conjugate shortcut says if you have something that looks like this, let's go with 16z squared minus 25 q squared. If you had that problem to factor, you can use the example C on your worksheet, which says that your answer ought to be in the form first minus last, first plus last. In other words, the conjugate rule. So that would suggest that since this is a perfect square, that's a perfect square, a minus in the middle, that we can have this format. Well, what is this first term? It is 4z squared. This last term is 5q squared. So I have a first term perfect square. I have a last term perfect square. So my answer then is 4z minus 5q, 4z plus 5q. Okay, so that's your, those are your A, B, C, D shortcuts. Now let's look very briefly at the D and E shortcuts. Okay, that basically says that if you have a first term cubed plus a last term cubed and also first term cubed minus last term cubed, two different problems, then that's equal to the first term plus the last term. Okay, as you see these, you've got first term times last term. And then you've got some more to follow on. Where did my sheet go? Because I'm wanting to show you this. Okay, here's the sheet we're looking at again. And now we're looking at this rule E and F here, dealing, or D and E rather, dealing with difference of cubes or sum of cubes is what that's called. This example C and D. Now, as I was saying on this one, the rule tells me that I'm going to have a product of two terms. First term squared, opposite sign minus first times last plus last term squared. Notice these drop one power because we've taken one power out of them. Notice this sign is the same as that sign, and the following sign in the middle is minus, and there's no 2 in front of it like there is in rule A and B. Now, this piece will never factor. It can't. Okay? The only way you could solve that is if you wanted to use quadratic formula. Well, anyway, what if this is a minus here instead of a plus? Then you're going to have first term minus last term, and then you're going to have first term squared plus the opposite sign, first times last, plus last term squared. Now, what if I had the problem 8x cubed plus, let's see, 27y cubed? Okay, well, my first term is 2x cubed. My last term is going to be 3y cubed, because cube root of 27 is 3, cube root of 8 is 2, cube root of x cubed is x, cube root of y cubed is y. So now, what is this thing going to equal? Using this format, I'm going to have 2x plus, since this is a plus, okay, and I'm going to have 3y. Now for my second part of this, I'm going to have the first term squared. Okay, I'm going to write this down in two terms, minus the first times the last okay, plus the last term squared. Now, I don't care whether you write this step or not, but this is certainly what you have to be thinking. So your final answer then is 2x plus 3y times 2 squared is 4, x squared is x squared, 4x squared, minus 2 times x times 3 is 6, times y is 6xy, plus 3 squared is 9, y squared is y squared. So here would be your, this problem in factored form. Any questions about that? If not, well, then we'll go on. Actually, I think I want to take a picture of this. Might be useful later. Except I gotta get my shadow out of the way. Okay. Now, that said, we'll go on to the continuation of where we were, but I needed to spend some time on these shortcuts. All right. Before I go any farther, I want to mention, now it's both in the announcements and it's in the assignments. In your packets, page 34, 35, 36, 37. Now you notice I have some problems circled. It's not circled on your packet, but listed in the both the record sheet and listed in the announcements and the assignment are the problem numbers that you're supposed to work. There are only about 40 of them that you have to do, not this 108. I would like you to have those completed before class on Friday so we can go over these. Then after we go over them, you're going to have a chance to rework all of the problems up until 10 p.m. Friday night, and then they have to be pictures of your scratch work, and your answers are going to have to be uploaded to Blackboard in a PDF form like we did on the information sheet, and that has to be by 10 o'clock Friday night. Okay, so let's go on. We've covered discriminant already. Remember, it's only the part that's under the radical, under the quadratic formula. So let's go into doing the next thing we want to do. And I think, okay, so now we're in solve the equation for a specified variable. Well, if you recall, this we've called virtual equations. We've called them literal equations. Basically, we've got to isolate an A out of this equation, is what we're doing. So what we do is first get the A by itself, and then find 1A. Okay, here's the A by itself. We move the B over to the other side. Now we can divide both sides by 4. In this case, since 4 is a perfect square, you wouldn't have had to have done that. You could have taken the next step before you did that. Okay, so here We take the square root of a squared, we take the square root of all of that, which gives us this value. Now, there are 3 rules for simplifying radicals, okay? And there's the plus minus there. My string is kind of in the way. Those 3 rules are: 1, thou shalt not leave a perfect square under a radical. I got a perfect square right there, I can't leave. Thou shalt not leave a fraction under the radical. I've got a fraction, I can't leave it that way. Okay? Thou shalt not have a radical in a denominator. Well, I don't have that in this case. So what do I need to do to this thing? Well, first I can extract this 4 and get a 1/2 out here in front of this. B squared plus 8. Now, b squared plus 8 will not factor in any way, shape, or form. It's not a perfect square, okay? There's really nothing we can do with it, so then this should be our answer. Now, they show it, I showed it as 1/2 times the radical. They're showing, oh, I left off my plus or minus, excuse me. And they showed it as over 2. You can leave it either way in this one. It's not imaginary, so you don't have to uncommon denominatorialize it. Okay, next problem. In this one, we want to isolate 1x. So we got to get the 2 pi on the other side. How do we do it? Since it's multiplied times the x squared, we got to divide both sides. When we divide 2 pi by 2 pi, it cancels. When we divide v by 2 pi, that's what we get. Now I've got to take the square root of both of these. Plus or minus. Notice the plus or minus goes on the one I'm not trying to solve for. So, and I've shown it here again. So that gives me square root of x squared is x. Square root of v over 2 pi is plus or minus square root of v over 2 pi. On this one, how do I get rid of this 2 pi? Inside here, I multiply by 2 pi over 2 pi. That's like multiplying by 1, which we can do any time. And this, by the way, is under the radical that multiplication is. Now, when that happens, the square root of 2 pi squared is 2 pi. So basically what you're doing here is you are extracting that to 2 pi, which is in the denominator over there. Okay? So that would be your final solution on this particular problem, as far as you could take it. You do some erasing here. You notice I changed up here a little bit so we can see the full screen now with very little loss. Okay. Here's a word problem. If an object has an initial vertical position of s sub o and a velocity when you first launch it of v sub o straight upwards or downwards, what in the heck are they talking about? If I shot an arrow into the sky, never would I know where it would lie. Well, actually, you can figure that out mathematically. Now, the vertical position is I'm not shooting from ground level. I'm not pulling my arrow from ground. I'm pulling my arrow from approximately 4 feet or about 5 feet right here. Okay? And then how hard I release that arrow is the velocity it's talking about when it first leaves the strings on the bow. Okay? And here's a formula that will tell you. By the way, anytime you see a t squared in a problem like this, in a t, it's almost always a gravity problem, because gravity is a function of time in terms of how fast it falls. Now, here's the formula. How did they get this formula? By repeated trials and making tables and working it out. Now, g is the acceleration due to gravity, which is 32 feet per second per squared, or 9.8 meters per second. T is the time of travel, okay? Time of travel, second squared. Now, I'm not expecting you to know this, and I don't even really want you to take these notes down. But I just want to show you a little bit through here. Okay, they're giving you some data right here, some information on the force of gravity, 32 feet per second. The initial velocity was 20 feet per second, and it was 6 feet above ground where they launched it. So they started filling in the information, okay? They don't know how long this thing flew. Well, they've simplified the equation, and over here is a graph. You're standing right here and you launch the arrow like this. At some amount of time, which in this case is about 0.6 seconds, it's going to meet its greatest height. Then after that, it's going to start falling. And it'll be here at 1 second and on down and end up here. That means its total flight from here to here was 1.5 seconds. Its total height of flight was 1,200 feet, assuming these are hundreds. Okay? That's the way that works. By the way, that's the same way that it works when you take a pill. When you take that pill, there is 0% in your body of the medicine. You would start here. Now, I'm just going to use this same graph. But when you take the pill, there's 0% of medicine in your body. In an hour, you're going to hit the peak of how much of that has dissolved and gone into your bloodstream. And then after that hour, the amount that's left in your bloodstream, whether it's a painkiller or whether it's any kind of med, will gradually taper off until it no longer has effect. So this is used in medicine as well, and determines how many if you have a 500 milligram pill, it might be this way. If you only have a 2 milligram pill or 200 milligram pill, then it might look something like this, where here is your maximum dosage. So at any rate, this is used, it's also used in radiology to determine how much radiation they should give a patient to not kill them. So those are just some of the uses of these quadratic equations. Well, they went through and solved it, and it's just a matter of the algebra we've been doing to get it. Okay, now let's go into our next topic. I better watch the time better today than I did yesterday. By the way, let's see, Desiree was the last one who came in. Hello. So let's go through this, see if I can find my clicker where I've laid it down up here, and see what we're going to do. Now we're going to solve polynomial equations. This time, you notice I've got this one that has 4 terms in it, and its first one is a cube. To solve this equation, we're going to use a process called factoring by graphing, or not graphing, but by, I'm having a senior moment right now and I can't think of the word. First thing they did, they saw if they could factor out a common term, and there is none for the whole thing. However, if you break this into 2 parts, the 8x cubed plus 4x squared, you can factor a 4x x squared out of both of those. And that's what it's showing that they did here. This is called factoring by grouping. Okay? The step that they did not show you in this problem, that should have gone between that and this, should have been 8x cubed plus 4x squared plus negative 50x minus 25 equals 0. Now, I had to put a plus in front of this so I didn't have to undo those. Now, I could have also, actually this should have been a plus there. If I left this a minus right here, I would also have the issue of, if this minus stayed here, then that sign would change and so would this sign. But anyway, here I have my 2 groupings that I'm going to now factor this group and factor that group. So we factored a 4x squared out of this first part. We factored a negative 25 out of both of these. Okay? Now, what does that give me? This one I just bring down. But I've got a 2x plus 4 before. Okay, I've got a 2x plus 4 in both of these terms. So I factor out that 2x plus 4 right here. Since this is a product here, I also have this 4x squared and that negative 25, because I factored these out of that. So that leaves me 2 terms. Now, what do I do with those 2 terms? This one still factors some more. Perfect square on the front, perfect square on the back, minus in the middle, gives me a 2x plus 5 and 2x minus 5 out of this. So now what I've got is I've got these 3 terms, and I have to use the 0 products rule. This one gives me this equation, and that equation, and the third equation. I get negative 1/2, I get negative 5/2, I get positive 5/2. Because I have a third power, a cube root or a cube up there, that's why I have as many as 3 answers. I could have fewer, but I can have at most 3. If I had a 4th power up there, then I could have 4 answers. But this method is called graphing by grouping. And problems 3 through 7 on that handout, which you actually don't have to do, but the problems 3 through 7 are this type of solution. Okay, now, what do we got here? I don't know if you can see my pointer. We've got a perfect cube on the front, a perfect cube on the back, a minus in the middle. So we're going to use our rule D and E off of my worksheet. First term minus last term, first term squared, plus first term times last term, which is 1. Notice the sign change, and then last term squared. Okay? Well, this first term gives me that. To get this, we have to use the quadratic equation. And they're solving that with the quadratic equation down here. Okay? So, what is my answer? 1/2 is one solution, and this is my other solution. Why did there's a problem with this though? That is not in A plus BI format with an I in it. So I would have to make this -1/4 plus or minus 1/4 I radical 3. Okay, what about this one? Well, whoops. If I wanted to solve this problem, first thing I do, w to the 4th minus 27w, okay, equals 0. I would factor a w out of both of these, and I would have w cubed minus 27 equals 0. Okay, now this, that gives me w times w minus 3 cubed, w cubed, times w squared plus opposite sign 3 times w minus 3 squared is 9 equals 0. Okay? This is going to give me w equals 0. This is going to give me w equals positive 3. This, we would have to use the quadratic formula to find out what its value is. And it will be with an imaginary number because this thing is prime and won't factor. So that's how you would work this problem. Now let's go into rational equations. I've got 1 over x minus 1 minus 2x over x plus 1 equals 2 over x plus 1. Okay, I've made some notes on this one already. We've got a disclaimer. I talked to you about that before, a domain check. We can never have a 0 in the denominator. So if x is positive 1, 1 minus 1 would be 0. So x cannot be positive 1. Likewise, if x is negative 1, then we would have a 0 again. So x can't be negative 1. So we've got to watch out for those disclaimers anytime there are variables in the denominator. Now, our common denominator is going to be x minus 1 times x plus 1. So we're going to multiply that common denominator times all three of these terms. Here it is. They're just going to show it as a distribution at this point. We're going to see if we can do some canceling. Okay. When I take these two times this term, the x minus 1's cancel, and I am left with x plus 1. When I take these two times this, the x plus 1's cancel, and I'm given 2x times x minus 1. So 2x times x minus 1. When I take these two times this one, the x plus 1's cancel, and I get 2 times x minus 1. Now we've got to distribute these two sets, and we've got to combine like terms. Now we're ready to get variables on one side, numbers on the other side. Remember, you cannot add x squares and x's. They're totally different values, okay? Because the x squares are a much powerful number than just a plain x. Well, when we do this, and we move everything onto one side, we've got that. Actually, what they did is they moved these three on this side. So, this thing will factor. It'll factor into 2x minus 3 and x plus 1. Those are the factors that it'll get. Now, this is 3 halves. You can't tell it. 2x minus 3 equals 0. Add 3 to both sides. 2x equals 3. Divide by 2, and you get 3 halves. You get that answer. This one, you would get a -1. Well, -1 is a value we can't have, so we have to throw this one out, because that would give us an imaginary number. This work is all down here. So, what is our final answer in this one? Generated from this factor, x plus x equals 3 halves. Okay, here's another similar problem. 2 over x plus 3 minus 2 over x squared plus 2x minus 3 equals 3x over x minus 1. Okay, we've got to factor this denominator. We find out when we factor this middle term that it's made up of x plus 3 and x minus 1. So we've got an x plus 3 there, x plus 3 times x minus 1 here, and x minus 1 here. So there's my common denominator. And I multiply it times every term, by distribution in this case. Okay, the x plus 3's cancel, leaving 2 times x minus 1. Both of these cancel both of those, so I've just got the -2. Out here, the x minus 1's cancel, so I've got 3x times x plus 3. I distribute, I simplify, okay, and now I have to refactor. So what do I get? It factors into these two terms. So this is going to give me an x, this x is going to give me -1, and this is going to give me -4/3. -4 on both sides, then divide by 3. -4/3. Here we are, -4/3. -1. I check my domain values that it cannot be. It can't be +1, and it can't be -3. Neither of these fit that, so we're okay. So my solution then is -4/3 and -1. And that's a pretty good place to stop with just one final comment. On these rational problems, we've been following a certain procedural number of steps. The first steps we've done is find the least common denominator, find the disclaimers, the ones that you can't be, the domain check. Now, in the process of finding the common denominator, you may have to factor some terms first. Okay, it depends on the problem. Well, after you've found your common denominator, you multiply it times every term. Then you distribute, simplify, cancel wherever you can, and then get it down to a simple equation to once again factor and solve. So that's kind of your steps. Factor, find the least common denominator, multiply times every term, do a whole bunch of simplifying, refactor if you have to, then get your solution. And that's the repetitive process on these rational expressions like this. With that, we got about a minute left, so I'm going to say have a great day today, and we'll see you tomorrow. If any of you have a question, you can always, of course, write a chat comment down at the bottom, and I'll look at it. Otherwise, you're welcome to sign out. I'll wait until all of you sign out before I sign out myself, just in case you are writing a chat comment.